Before you skip this, did you know that by next year, we'll be drowning in 2.2 billion tons of plastic waste? That's a $375 billion problem every single year. But here's the twist. Artificial intelligence may hold the secret weapon to crack this crisis wide open. We're not just talking better recycling, we're talking machine learning systems that can see waste in a whole new way, making recycling faster, smarter, and maybe even flawless. In this episode of The Deep Dive, we're revealing how AI is already transforming plastic recycling across mechanical, chemical, and even biological methods, and some of the breakthroughs, like machines hitting near-perfect sorting accuracy and enzymes engineered to eat plastic 38 times faster, are nothing short of jaw-dropping. Here's the catch. Most people don't know this is happening right now. And if you don't hear it here, you'll miss the story that could change how we fight one of the biggest environmental threats of our time. So don't just wonder, hit play and listen to the full episode now, before everyone else is talking about it.
Welcome to The Deep Dive. Today we're tackling something huge, and honestly it's getting bigger every year: plastic waste. Think about this number. By next year, globally, we're looking at maybe 2.2 billion tons of waste annually. The cost, a mind-boggling $375 billion just to manage it. And this isn't just about overflowing landfills, it's hitting our health, our planet. So the really big question we're asking today is, can AI, can artificial intelligence actually give us a powerful answer to this massive problem?
That's exactly what we're diving into. We're focusing specifically on machine learning and how it's starting to really transform plastic recycling. And we're not just talking small improvements here.
Right.
We mean intelligent systems making recycling fundamentally more efficient, way more precise, and ultimately sustainable across all the different ways we recycle plastic.
And for this deep dive, we've got some great material. We're drawing from a roundup of the very latest developments in ML for recycling systems, plus a really fresh review paper that looks closely at machine learning in thermoplastic recycling that's mechanical, chemical, and even biological routes. So our mission today, let's unpack the key insights, find those surprising facts, and really nail down the aha moments, showing how machine learning is becoming, well, maybe the ultimate partner in fighting plastic waste. Let's get into it.
Okay, so first things first. Why is recycling so hard? Especially plastics. I mean, even though recycling rates are going up in some places, we're humans, we're just creating more waste than ever. A huge part of the problem is just how expensive and difficult it is to separate the recyclables from everything else.
The sorting nightmare, yeah.
Exactly. Plus, there's often a lack of public awareness about what goes where, So the traditional methods, they're just not cutting it anymore. They can't handle the scale or the complexity. It's messy.
Literally messy.
Yeah. So automated intelligent systems aren't just nice to haves. They're becoming absolutely essential if we want to manage waste effectively.
When we talk plastics, thermoplastics are a really key target, aren't they? It's worth reminding ourselves why.
Absolutely. Plastics aren't all the same. Thermoplastics, unlike thermosets, have this unique ability that can be melted down and reshaped again and again without their basic chemistry changing much.
Like melting ice and refreezing it? Still water?
Precisely. Which makes them perfect for closed-loop recycling, where a plastic bottle can actually become another plastic bottle, ideally multiple times. That's where the real value is.
And this is where machine learning comes in, right? As a branch of AI.
Exactly. Machine learning is different from standard programming. It learns from data. It finds patterns and makes decisions based on those patterns. For waste, this means it can learn to separate complex, mixed-up waste streams far better, far more accurately than humans ever could. It's like teaching machines to see waste in a whole new way.
Okay, so let's get into the process. Pre-treatment, sorting. This seems like the first big hurdle. Everyone says separation is the critical step.
It absolutely is.
Yeah.
Because contamination is the killer. One wrong item tossed in the recycling bin can basically ruin an entire batch of good material.
And then it just ends up in the landfill anyway. Defeats the purpose.
Completely. And this is where machine learning algorithms have just, revolutionized sorting precision. Let's talk visual sorting first. We use things called convolutional neural networks, CNNs.
Okay, like advanced image recognition.
Yeah, think of it like that, but super powered. They classify and spot objects incredibly well. We've seen examples like autonomous robotic systems using CNNs getting 96% overall accuracy sorting cartons and plastic.
And 86%, why?
And there are even improvements on CNNs, like something called called a capsule neural network, hitting over 96% accuracy detecting materials from public bins, which are notoriously messy.
Right.
What this means for you is machines are getting really, really good at that first vital sorting step. Less good stuff gets wasted.
Okay, but this is where, for me, it gets even more interesting. It's moving beyond just looking at the plastic.
Oh, absolutely. Now we're using spectroscopy paired with machine learning. We can identify plastics based on their chemical makeup, their unique fingerprint.
Like seeing inside the material.
Kind of. Take mid-infrared MIR spectroscopy. You pair that with an ML model, like a random forest algorithm, and one study hit 100% classification accuracy for 5 major plastic types.
100%.
100%. And get this, it could even distinguish black plastics. Those are incredibly hard for traditional optical sorters because the carbon black pigment just absorbs the light.
Makes them invisible, basically.
Pretty much. Then you have near-infrared, NIR, spectroscopy, combine that with ML, and you can get over 95% accuracy sorting polyolefins, even with fairly simple prep work. It analyzes their molecular vibrations.
Reading their internal rhythm, almost.
Yeah, that's a good way to put it. And if you want to go deeper, look at the elements. There's laser-induced breakdown spectroscopy, LIBS-S. Paired with ML, it successfully identified 20 different types of virgin polymers, even with additives like carbon black mixed in. It shows it doesn't really care about color or pigments.
So the big picture here is we're layering technologies, right? Combining different sensors with smart deep learning to tackle these really messy mixed waste streams with incredible precision.
Exactly. It's sophisticated digital intelligence meeting a very physical, very complex problem.
Okay, so sorting is getting smarter. What about the next step? Mechanical recycling, the most common method.
Right, mechanical recycling. It's popular because it's generally cost-effective, simpler, and you can scale it up. But it's not perfect. The main challenges are degradation, the plastic quality can decrease each time you reprocess it, and variability in the final product.
Meaning the recycled plastic might not be as strong or consistent as new stuff.
Precisely. And this is another area where machine learning isn't just sorting, it's improving the actual transformation process, making sure that recycled plastic holds its value.
How does it do that?
Well, take regranulation melting plastic down into pellets. ML models can actually predict changes in things like molecular weight and viscosity during that process.
Which tells you about the quality.
Exactly. A type of model called a support vector regressor, or SVR, has been used effectively for polyethylene, predicting these properties. This helps maintain quality, stop the plastic getting too brittle or weak.
That's crucial.
And for overall quality control, something called transfer learning is a huge help. Imagine you have an ML model that's already learned tons about new virgin plastic.
Okay.
Transfer learning lets you adapt that knowledge quickly to recycled materials, so you get faster model training and better predictions for quality in processes like injection molding.
So you don't need massive new data sets for every recycled batch.
Ideally, no, it speeds things up. And we're seeing ML algorithms predict specific properties with amazing accuracy, like tensile strength, how much you can pull it before it breaks. Some models achieved an R2 score of 0.96, predicting this for plastic films.
R2. Remind us what that means again.
Right, sorry. An R2 of 0.96 basically means the model can explain 96% of the variation in the material's strength. It gives engineers huge confidence in using that recycled material.
Got it. High confidence.
Yeah. And other models, like artificial neural networks, are predicting and even optimizing things like strength, flexibility, density, and recycled PVC based on what went into the mix. This lets you actually design materials from waste. And for managing batches, ML has shown it can cut down the property variations in recycled polypropylene by over 46% in some cases. Much more consistent product.
Okay, that's mechanical.
Yeah.
Let's shift now to chemical recycling. This sounds more intense, breaking polymers right down.
It is. Chemical recycling breaks polymers into smaller molecules, sometimes all the way back to the original building blocks, the monomers. It allows for potentially higher value reuse. Think of it like taking Lego bricks apart completely.
But it's complex, right? Especially with mixed plastics.
Very complex. Mixed waste is a challenge, and you often need very specific catalysts to make the reactions work efficiently. And guess what? ML is proving vital here too.
How so?
Take pyrolysis heating waste without oxygen. Using advanced ML like deep reinforcement learning combined with other network types, researchers increased the yield of valuable light products from pyrolyzed plastic oil by over 50%.
50% more useful stuff. How does that work, like the reinforcement learning part?
It's a bit like teaching an AI to play a game by letting it try millions of strategies. It learns through trial and error, figuring out the absolute best conditions, temperature, pressure, catalysts, to maximize the yield of the chemicals you want.
That's clever.
It is, and other ML models are showing incredible accuracy R2 scores around 0.98 in predicting exactly what kinds of liquid fuels or chemicals you'll get from pyrolyzing different plastics.
So you know the output before you even start.
Pretty much. And in gasification, turning waste into syngas fuel, ML is optimizing the gas composition, its heating value, the overall efficiency. We're seeing models for PE gasification with R2 values over 0.99 for predicting energy output. That's near perfect prediction.
Almost perfect, wow.
Yeah, similar high accuracy for predicting syngas from mixed waste. Even predicting hydrogen production from rubber and plastic waste mixes with R2s of 0.99.
So huge progress in pyrolysis and gasification with ML. But you mentioned before there's a gap.
There is. Right now, there's surprisingly little research using ML directly for other key chemical methods like depolymerization or solvolysis. These hold immense promise, so it's a big area for future work, definitely.
Okay, noted. Now what about biological recycling using enzymes?
Yes, enzymatic hydrolysis. This is a really exciting area. It uses enzymes, nature's catalyst, to break down polymers. It's often a milder process than chemical methods.
And ML is involved here too, not just optimizing processes, but designing the actual enzymes.
That's the truly amazing part. ML is getting right into the biology. We're using complex models like 3D CNNs and transformer models similar to those used in language processing to understand enzyme structures and sequences.
To make them better at eating plastic.
Essentially, yes. By identifying patterns, these models can predict modifications that enhance an enzyme's ability to degrade plastic. For example, one ML system called MUT Compute helped find variants of a peat-eating enzyme that were up to 38 times more active and worked at higher temperatures.
38 times faster.
Exactly. Another model helped discover a variant called tobopatase that significantly improved peat breakdown. This is radically speeding up enzyme discovery. We're talking years of lab work potentially condensed.
Incredible. What else can ML predict about these enzymes?
All sorts of crucial properties. How fast they work, turnover number, how strongly they bind to the plastic, Michaelis constant, their selectivity for specific plastics, their heat stability. One model, XGBoost, achieved over 90% accuracy predicting if an enzyme could degrade a specific plastic just from its protein sequence.
So you know if it'll work before you even make it in the lab.
That's the goal. And large language models are even predicting the best pH conditions for enzymes to work in. Then, for optimizing the actual reaction, algorithms like Bayesian optimization are used to fine-tune things like temperature and enzyme concentration, achieving huge increases up to 360% higher turnover compared to traditional methods.
So much less enzyme needed for the same job, basically.
Really, much more efficient.
Okay, we've seen ML transforming sorting, mechanical, chemical, and biological recycling. But let's talk about the data itself. How do you actually teach these machines? You mentioned feature engineering. What does that really mean?
Feature engineering is crucial. It's about preparing the raw data so the machine learning model can understand it and learn from it effectively. Think of it like highlighting the important information. If you were teaching a kid about apples, you wouldn't just show them an apple. You'd point out it's red, it's round, it's smooth. Those are the features.
Okay, makes sense. So what are the features for recycling data?
It depends on the stage. For spectroscopic data, those light fingerprints we talked about, it involves cleaning up the signals, using techniques like scattering corrections, normalization, maybe reducing the complexity, using methods like PCA, principal component analysis. It turns noisy data into clear patterns.
Got it. What about process data?
For things like temperature, pressure, flow rates, you usually standardize them. Put them on a common scale so the model isn't biased by one parameter having much larger numbers than another.
Right. Fair comparison.
Exactly. For polymer properties, you use numerical ways to describe the molecular structure or how it flows when melted, its viscosity or its thermal properties. And for enzymes, you have to turn those long amino acid sequences into numbers, into vectors that capture their function. Techniques like sequence embeddings do this.
So translating biology into math the computer understands.
Pretty much. Then you often use methods like mutual information or SHEP to figure out which of these features are most important for predicting the outcome. It helps the model focus. And finally, there's transfer learning again, using knowledge from models trained on new plastics to help understand recycled ones, saving a lot of data collection effort.
It's clear machine learning is bringing massive potential here, a real game changer, as you said. But it's never that simple, is it? There must be challenges alongside these opportunities.
Oh, absolutely. It's a powerful tool, but not a magic wand. On the opportunity side, things are moving fast. We're seeing ML models getting smarter by incorporating insights from physics and chemistry simulations, so-called physics-informed ML.
So they understand the underlying science better.
Right. There's also huge potential to embed these pre-trained ML models directly into recycling machinery extruders, injection molders. Imagine a machine that optimizes itself in real time based on the material it's processing. That's a big competitive edge.
Intelligent factories, basically.
Exactly. And we're moving towards collecting data across the entire recycling process from start to finish to train deep learning models for optimizing the whole system, not just one step. Plus, while there's a need for more ML experts in this field, we're also seeing more user-friendly ML tools emerge, making it easier for existing engineers and technicians to use this tech.
Okay, but the flip side, the challenges.
Data is still a big one. Many studies use fairly small data sets, which makes it hard to know if the model will work well on different waste streams or in different factories. We desperately need larger, standardized, shared data sets, maybe even high-quality synthetic data.
And the black box issue.
That's another key challenge. Some of the most accurate models, like deep neural networks, are very complex. It can be hard to understand why they make a particular prediction. That lack of interpretability can be a barrier to trust, especially in industry.
People want to know how it works.
Understandably. Then there's just the sheer messiness of the real world. Contamination in bins because people don't sort right, the difficulty finding people for manual sorting jobs, the endless variety in waste, different shapes, sizes, colors, combinations. Training a robot to handle all of that, 247, with high precision is incredibly tough.
They need millions of examples for every new thing.
Pretty much, yeah. And a model trained for one type of plastic or one recycling method might not work well for another. That's the transferability issue. Plus, with limited data, there's always the risk of overfitting. The model learns training data perfectly but fails on new, unseen data. And, as we mentioned, some key chemical recycling areas are still really underexplored by ML.
So wrapping this up then, machine learning isn't replacing the need to recycle, but it's making it vastly smarter.
Profoundly enhancing it, I'd say. Optimizing every stage from that initial sort through the physical and chemical changes, right down to designing the very enzymes that break plastics apart.
The progress is undeniable. Near-perfect sorting for some plastics, boosting enzyme activity sometimes hundreds of times.
Yeah.
It really feels like we're leveraging intelligence in a new way to tackle a massive physical problem. It leaves you wondering, as machine learning keeps getting better, keeps learning, what other innovations are just around the corner for waste management? And maybe more importantly, how can we all play a part in accelerating this journey towards a truly circular economy? Something to think about. Join us next time on The Deep Dive.
You've just watched an episode of Deep Dive, our AI-powered podcast where two AIs explore the frontiers of finance, economics, and machine learning. If you found insight here, share it. If it helped you think sharper, like it. And if you want more deep technical conversations, subscribe and tap the bell so you don't miss the next drop. It's a podcast on how to apply AI and ML in finance and economics by two AIs, supervised by a senior portfolio manager from top-tier asset managers. Stick around. The future of investing is already speaking. Liked how that paper got decoded? We've spent 20+ years turning machine learning and AI into real-world tools, not just slide decks. Whether you want to implement a model, validate research, or build something from scratch, we can help. Explore our showcases to see it in action. Visit our site or contact us directly. Let's turn complex ideas into working intelligence together.